Section 11.3, Stellar Evolution. We're going to focus on stars like our sun. That's the one we are most interested in. And we already know that our sun is a main sequence star. Now, what does that mean? A main sequence star, of course, on the HR diagram. The HR diagram is that plot of the brightness of stars versus their temperature. And a main sequence star can kind of be thought of like a person from the age of 5 to the age of 65. The vast majority of that person's life, all of their education and all of their career years. Okay, section 11.3, Stellar Evolution. I'm going to focus on stars like our sun, since that's the one we are most interested in. And on an HR diagram, our sun falls on the main sequence, like most stars. An HR diagram, you may recall, is a plot of how bright stars are versus how hot they are. And most stars behave exactly the way you'd expect. Hotter stars are brighter and cooler stars are more dim. A star like our sun will spend actually about 90% of its lifetime on the main sequence. I like to give the analogy, it's kind of like a person, a human being from the age of about 5 to 65. All of the education and the career of a person's life, the majority of their life. In this case, the star is very stable, and it's converting hydrogen into helium. For a G-type star, like our sun, that time period is about 10 billion years on the main sequence. Our sun is 4.6 billion years old right now, which means our sun is kind of a middle-aged star. There are stars that actually spend much less time on the main sequence, hotter stars that burn out faster. And at the other extreme, the least massive stars, the least hot stars, the M-types, they can stay on the main sequence possibly up to 1 trillion years. It's pretty amazing. As a matter of fact, every red dwarf that's ever been created in the universe is still burning. None of them have evolved. And the reason is the universe is simply not old enough at this point for those stars to have evolved to the next level. It's just pretty amazing to think about that, for example, stars in the very, very first generation of stars, those red dwarfs are still out there burning today. Okay. Back to our sun, though. Any star that's on the main sequence is undergoing what we call hydrostatic equilibrium. That's this epic battle between gravity trying to crush a star and fusion trying to blow it apart. And it's amazing how stable stars are with this epic battle taking place. Our sun is very, very stable on a year-to-year basis. However, over time, our sun has changed over a long period of time. For most stars, and there are exceptions, but for most stars, the mass is going to determine its fate. And the key number, if you have to pick a number, it's not a really, it's not a very well drawn line in the sand, but somewhere around 8 solar masses. Stars that are about 8 times heavier than our sun and smaller are not going to go supernova. They're not going to blow up. Our sun will never blow up. Again, there are some exceptions, but for the most part, stars, and that by the way, includes 90-something% of stars. The vast majority of stars will not blow up. Ones greater than 8 solar masses, well, chances are they will blow up. From about 8 to 12, there's a chance they can kind of save themselves. But anything greater than 12, almost certainly then, those stars are pretty doomed, I guess you could say. Okay, so what happens then to this vast majority of stars if they don't blow up? What happens to them? Well, stars like our sun are going to become what we call a red giant. They become briefly what's called a subgiant and then a red giant. This entire transition only takes about 100 million years. What's happening is that every day our sun is building up helium in its core. But the problem is the sun right now is nowhere near hot enough to actually ignite the helium, to burn the helium. And so billions of years in the future, gravity is going to win the ultimate battle and start crushing the core of the sun. As it crushes the core, The area around it, which is still undergoing fusion, it's sometimes called the hydrogen shell, that area is actually going to burn hotter. As the core contracts, the area around it burns hotter. That's going to push out the outer layers of the star. And as the outer layers get pushed outward away from sort of the internal furnace, they're going to get cooler. I mean, that's why it's a red giant. The red color tells you that it's a cooler star. So it's a very strange dichotomy that's happening. The interior of the star is shrinking and getting hotter, while the exterior is actually expanding and getting cooler. And a star like our sun will actually swell up to about 100 times its current diameter in this red giant phase. A couple stars that are doing that right now would be Arcturus, famous for the arc to Arcturus that we learned about in chapter 1. Now, the thing about a star like Arcturus, I'll mention Aldebaran as well, which is in Taurus. It's the eye of a retirement age star. We're going to watch a little clip here showing what happens as the sun evolves in the future.
This is an animation of the death of the sun from a faraway perspective. As we zoom in, time passes and our sun evolves. In nearly 5 billion years, our sun will change into the giant red phase, eventually ending its normal nuclear burning cycle. Its core will contract, all the while its atmosphere recedes. Some of the terrestrial planets will likely be engulfed.
So here we see the sun swelling up. It already engulfed Mercury, Venus, and there goes the Earth. Looks like Mars is going to be just outside of where it swells up. Now, there may be some burnt cores left. Kind of some pieces of charcoal left over there of the inner planets. And then they kind of have a silly one here showing this transition from the perspective of the Earth. I think I'm going to skip that one here for this part. But anyway, this is something that the future generations would have to deal with way, way, way in the future. I guess we'll watch it here.
The evolution of our main sequence sun to its red giant stage would cause the daytime sky to change dramatically. Earth itself would also greatly change. The oceans would boil, the atmosphere would escape, the land would burn, and life would end.
Yes, not a cheery ending there for the Earth in that case. But there are some things we could do in that distant, distant, distant future, billions of years from now. Of course, by then, surely humans will have moved on to other planetary systems. You could also, if you were still left behind here on Earth, you could actually maybe venture to the outer solar system. Places like Titan might actually end up being pretty nice. Mars, for example. And there's actually a plan where you could possibly, for a short-term solution, actually move the Earth. That one's kind of interesting as well. Anyway, back to the story of our sun. As our sun's core gets hotter and denser, eventually it will get hot enough to fuse helium. That's called the helium flash. And when that occurs, when we say fusing helium, actually what nature does, it actually fuses 3 heliums together. And since helium's number 2 on the periodic table and carbon is number 6, 3 heliums fuse and make carbon. It's called the triple alpha process. There was kind of a nickname for helium particles long ago. They accidentally, mistakenly called them alpha particles. And so triple alpha really is kind of a nickname for triple helium process. And so it begins kind of a second main sequence. It's called the horizontal branch on the HR diagram. It's kind of a second main sequence. It's not going to last nearly as long as the original main sequence. Back to our human analogy, it'd almost be like a person in retirement who just takes on a small job to supplement their income in retirement. So these stars now start burning helium into carbon. They actually shrink it back down. They're not as large as they were in the red giant phase. And for a while, they're kind of steadily converting helium into carbon. But of course, that can't last forever. And the problem is that carbon starts building up in the core, and a star like our sun will never get hot enough to burn carbon and carbon. It can never fuse carbon that way. So the gravity, again, is going to win in the long run. Gravity starts crushing the core. The core, or the area around it, starts burning hotter, which pushes out the outer layers and makes them expand and get cooler. As Yogi Berra said, it's deja vu all over again. It's the same exact process that in which we made a red giant. Now we're going to make a red supergiant, and of course, as they get bigger, and even larger, of course, in the red giant phase. Now you could be hundreds of times the original size of the star, which is going to make the star much brighter. The most famous example by far is good old Betelgeuse, and I like to mention Antares as well, which is a beautiful orangey star in the summertime sky looking south right in the heart of the scorpion. Those stars are hundreds of times wider than our sun, but that just means they're retirement age stars, and they have gone through this transformation. Okay, we'll end. I often get students often ask me, are Betelgeuse and Antares the two largest known stars? No, they are not. Let's take a look. I don't know if it still holds the title, but for a long time, VY Canis Majoris held the title as the largest known star. And as you can see, looks like